So thanks for coming today. I'm really happy to see all of you. I'm glad that the turnout is so good on this lovely afternoon. So thanks for taking some time out of your day to be here, talk about earthquakes. And of course, this is in honor of Volcano Awareness Month, which we have every January. And so this is just one of a series of talks, as well as other programs that are going on throughout the month. And at the end, I'll share a few of the upcoming ones with you. So the purpose of the talk today is just to discuss earthquakes here in Hawaii. Why do they happen? Where do they happen? What can you do about it? I'll give you a preview of some of our analyses from the 2018 eruption earthquakes as well, and a little bit about what we do in the USGS. If you have questions, or if I say any terms that you don't know, just raise your hand, let me know anytime. It's fine to interrupt me, and we'll also have plenty of time at the end to ask more in-depth questions too. A little about myself first. So my name is Brian Shiro. I've been with the Hawaiian Volcano Observatory now almost 4 years, where I coordinate the Seismic group there, where we monitor the earthquakes here on the island. Prior to that, I spent almost 11 years at the Pacific Tsunami Warning Center on Oahu, where I was involved with monitoring earthquakes and tsunamis around the world, and have managed seismic networks in different places, including Fiji and Tonga and Antarctica, Marianas, Canada, as well as here in Hawaii. And the art and science of monitoring earthquakes is something that I find enjoyable. And if you have questions about that, we'll touch on it here, but just a little bit. Okay, so earthquakes in Hawaii. Hawaii has thousands of earthquakes every year, and in fact, in any given day, you may have hundreds. Here's an example of a station in the East Rift Zone of Kilauea, which recorded, as you can see, each one of these blips on the graph is an earthquake. This was actually on May 2nd of 2018 in the lead up to the eruption, which happened the next day in the Leilani Estates. And of course, in this example, this is highlighting the importance of monitoring earthquakes to forecast volcanic eruptions and to help keep people safe from volcanic hazards. This and other stations like it were used to track the earthquakes going down the rift zone as they traveled from the area of Pu'o'o down to Leilani Estates, where the lava eventually came out. So I thought I'd start off with grounding you where we are right now today. So this is actually a snapshot of earthquakes in the past week. If you want to know what's going on, you can also check out our website anytime, and you'll see a different representation of this. But what you can see here is the island, and the circles are earthquakes, and the color is how deep it is. The more blue or purple, the deeper it is. And one thing that you can notice too is if you took a big knife and sliced it like a cake, there's two cross sections here, one going east-west, which is as if you had sliced it and are looking toward the north. And the other one is a cross-section going north-south, as if you sliced it and were looking toward the west. So that's what this is showing you. You can see the earthquakes don't just happen everywhere. They have a certain geographic pattern. They're mostly on the southern part of the island. They're mostly around the active volcanoes. And they're mostly shallow, with this exception here of this cluster that occurs around Pahala. We can advance that to show the last month. And if you're paying attention, you notice that at the top there were 400 earthquakes last week. This is magnitude 1 and greater. And here's the last month, 1,600 magnitude 1 and greater earthquakes. Now you can see starting to have more scattered earthquakes in the northern part of the island and the west side of the island where we are. And these earthquakes occur for different reasons. We'll get into that in just a minute. But you can still see the same general pattern, most of it happening in the south, most of it shallow, with that big exception here around Pahala. And in the last year, 10,000 earthquakes. The longer you go, the more you're going to cover up the island with dots. And I think you all know, everybody has probably felt an earthquake, right? Can you raise your hand if you felt one? Yeah, almost everyone, I'm sure. Living here, we know it's earthquake country. Earthquakes happen all the time. So this video is 3 minutes long, and it gives you an overview of the different types of earthquakes. There's 3 types. There's going to be a quiz. How about that? So this video, by the way, you can find online. It's produced by an organization called IRIS with cooperation from us. And if you slice the volcano in two, you can see a cartoon view of the magma coming up The first type of earthquake that happens here is related to the volcanoes directly, related to magma and gases moving underground. And as the as the magma forces its way through these conduits, it breaks the rock. And anytime the rock breaks, you have an earthquake. So here's an example where the magma just made its way out here and erupted. Now, these other lines here represent faults along the flank of the volcano. Who's been to the park and driven down Helena Pali? And those big faults. Here's a zoom in on that. That is slipping all the time, and as it slips, each time it does, that's an earthquake. And so those are tectonic kind of earthquakes. That's the second type of earthquake we have here, just along faults, not due to the magma or the gases, just due to settling of the island. That's the most numerous type of earthquake in Hawaii. Happens the most commonly, and it's the most dangerous potentially, if this lower section goes. So this red line here is the boundary between the volcanic material above that rests on the older ocean floor below. They're made of different types of rock, and the two slide along each other pretty easily. And so when this gets pushed, or when this moves, like happened in the magnitude 6.9 earthquake on May 4, 2018, this can produce very big earthquakes, which we'll talk about a little bit more, including the 7.7 in 1975. Now, the third kind of earthquake happens deeper down. Now, these are the kind of earthquakes that are more common around here, as well as Kohala and other areas of the island away from the active volcanoes. These are due to the bending of the plate beneath the weight of the island. So if you imagine all this volcanic material from all the volcanoes piling up on top of the Pacific plate over many years, it pushes down and it bends that plate. And that produces stresses, and occasionally it causes the rock to break and make earthquakes. So we call those flexural earthquakes, or in this video they call them mantle earthquakes. And those are the most common type of earthquakes up the chain as well, including these ones noted here, Lanai and Maui and Molokai, etc., some of which have been quite damaging. So the three types are the volcanic, the tectonic, and the flexural. We'll talk about hazard in just a minute. This is an older map, but this is showing the hazard's high on the Big Island, which we know. So this island, Earthquakes in Hawaii, it's available online. We'll link to it once this gets posted on the HBO website later. Maybe. Let's see if I can get this to work. There we go. Okay, remember the quiz I told you about? Let's try this. Who remembers one of the types? Volcanic? Okay. Tectonic? Mantle? Okay. Or flexure, right? The bending. So there's a volcanic. There's a little cartoon. This is showing, imagine a little finger of magma underground moving along. They call that a dike. And as it's forcing its way into little cracks, it's making them bigger, widening them, creating earthquakes as it goes. And usually in the very tip of that dike, you get what's called a high-frequency type of sharp earthquake. And then behind it, once the conduit is open, you get this resonance that happens when the magma and the gases just reverberate inside the pipe. And that's often called tremor. The second type, tectonic, as someone said, can occur on small faults or this really big fault beneath the island. And these are the most numerous type. And then the flexural, or the mantle, as the video called it, are the ones that occur deeper down, and they're due to the bending. And in fact, it's not only bending under the island, but it can be bending away from the island too, all the way out to Oahu. So that's why we have earthquakes here. That's what causes them. And even though we're not on a plate boundary, like California is, we have a lot of earthquakes. In fact, in the U.S., we have the third highest rate of seismicity in the country due to these three processes. So that gets us to earthquake hazards. What do we do about that? So this map shows earthquakes magnitude 3 and higher that have happened in the past decade, just the last 10 years. And you can see they're mostly on the Big Island. The biggest ones are on the south. The size of the circle is the magnitude of the earthquake, but they're scattered up the island chain. And now you know why, right? It's from the bending of the plate up there. And why 3 and higher magnitude? Because that's generally what you might feel, right? Do you guys feel very many earthquakes smaller than magnitude 3? Maybe if it's nearby, but generally it needs to be about that big to feel it widely. Now of these, some of them are larger and damaging. So this is showing magnitude 6 and greater earthquakes since 1868, okay, which predates instrumentation in seismology, but we have ways to figure out magnitudes for older earthquakes. And you can see a number of large damaging earthquakes. All these caused various amounts of damage. So in fact, by taking data like that, scientists have figured out that the probability of the next damaging earthquake, generally speaking, we have a damaging, if you define that as 6.5 or greater earthquake, every 10 years or so. We just had one, right, in 2018, the magnitude 6.5. Who knows the prior one before that? Kīholo Bay, right? 2006, exactly. So 2006 to 2018, it's roughly that much. But you can see, and the probability gets higher and higher the longer you wait. In fact, remember I mentioned our relative risk compared to other places in the U.S. So here's a map of the country. You can see the red color along the west coast, Alaska, southern Hawaii, as well as Puerto Rico. So those are the areas with the highest hazard to earthquake. Okay, so when these big earthquakes happen, they rupture a fault. So a fault is the place underground where the rocks slip to make the earthquake. And if you've ever bent and broke a pencil, you know the phenomenon of bending it a little bit and it won't break. It just bends and it goes back to where it started, right? And that's what's happening to the Earth all the time. There's a little bit of stress, bending the rock a little bit, but it doesn't break. But if it bends it long enough and persistently enough, eventually the rock can't sustain that anymore and it snaps, right? That's a brittle process, and that's what happens in the Earth as well. And of course, when that happens, it happens along a surface. We call that a fault. So that's just in the case of a pencil, would be the width of the pencil. And so what this is showing is the fault areas of some of the largest earthquakes that have affected the island here. And a lot of them are just rectangles because we're just roughly guessing, based on the energy released, how big the fault would have to be to produce that energy. But in the case of the 1868 earthquake, which is this odd shape here, we think it ruptured this whole section of the island, which is almost the whole south flank of the volcano. And based upon that, seismologists think that the largest earthquake that can happen in Hawaii is about a magnitude 8. That was a 7.9 earthquake and was almost the whole south flank. So if just a little bit more ruptured, maybe you can get up to an 8, but not anymore. And that's just due to the physical geometry of the island, how big it is. And again, in the video, remember the red line in the video showing that surface between that big fault between the upper material that's younger and the older material below. This is that area moving. That's what that is. So I'm going to go through just a few examples of these historic events just to give you a feel for what they were like. The 1868 earthquake, the Great Kapaʻau earthquake, the one that I mentioned is shown here. This is its shake map, which is a depiction of the intensity away from the earthquake. So the earthquake happened down here, and the intensity is how much ground shaking you get away from the earthquake. And it's measured with these Roman numerals, and traditionally was qualitative based on reports that people give about what it was like, what fell down, what kind of damage there was. And then today we augment that with actual measurements of acceleration of the ground as well. But you can see it rattled all the way to Oahu. In fact, even there were reports on Kauai as well. And here's a picture of a church that was destroyed by it. So certainly this is the biggest earthquake that has been recorded in Hawaii. This one was also notable because it created a local tsunami. And this tsunami unfortunately killed a number of people as well as some landslides. And so it's also the deadliest earthquake that we've had in modern times as well, or in recent times. Also notable from this earthquake, it's the only time it's been documented that it induced an eruption. So the eruptions in Kilauea and Mauna Loa were actually affected by the earthquake. So it's pretty interesting. So that there is an interplay that can happen between them. Since this is a Kona audience, I thought I'd talk about the 1951 earthquake. This was actually the biggest earthquake since the Kaʻau earthquake. So 1868 earthquake happened, and the next biggest one was 1951 right here in South Kona. And this one was quite severe, also produced a really small local tsunami that was not damaging. There were no fatalities recorded from this, but it was damaging. You can see, here's a picture of this is a water tank that was destroyed near here. 1975 earthquake. Who was around and felt that earthquake?
Yeah.
And the one that happened in 2018 that we just had was in almost the exact same place, almost a repeat of that earthquake, just not quite as big. But you can see some photos here. Here's things thrown on the floor at a store in Hilo, cracks in the national park, and the tsunami that it produced, destroying the house in this case. That tsunami was famous too for killing 2 Boy Scouts who were camping in the national park at the time. Finally, the 2006 Kīholo Bay earthquake, as well as the Mahu Kona earthquake. This is interesting because they were twin earthquakes that occurred not from movement along that fault at the base of the island, but this is due to that third type of earthquake from the video, the flexure or the bending earthquakes. So this little diagram below, you can see that is showing that the Kīholo Bay, the first earthquake, was actually in this lower part of the plate that was bent down and had the stresses pushing it more outward. And then the second earthquake, the Mahu Kona earthquake, was in that upper part, which had the stresses pushing inward on it. And we could tell that from the seismic waves that came from them. We could tell which way the fault moved and whether it was in compression or extension. And it was just a textbook example of that. And basically, the first earthquake triggered the second earthquake, and they were pretty close together in time. And who felt that earthquake? Most of you, if you were here. I was on Oahu and actually didn't feel it because I was running, but I saw a tree fall down on Oahu from that earthquake. Okay, so we have a lot of earthquakes in Hawaii, including a history of damaging earthquakes. And if you look at the magnitudes and energy releases of these earthquakes, they're on par with the biggest ones in the country, including the 1906 San Francisco earthquake, for example, which was very devastating in that city, as well as Loma Prieta, Northridge, famous earthquakes in California. Hawaii's earthquakes, just as big. The hazard here is equivalent to that. What's different is the population, right? A lot lower population, a lot less infrastructure. So there's less vulnerability, if you will, but just as much probability of the hazard. So, Kilauea eruption 2018 was remarkable in many, many ways. Most notably, of course, the volume of lava that came out. This is Fissure 8, and its lava channel, which fed a very vigorous eruption, covering so many homes and creating 800-something acres of new land to the island. But associated with that were a lot of earthquakes, although not associated with this process itself. So mostly earthquakes were earlier on due to the creation of that magma pathway in the ground that I showed in cartoon form, and then also at the summit, which I'll talk about in a moment. So if you break down the earthquakes, this is just a map of earthquakes during the eruption, magnitude 2.7 and higher, and if you, I like to break it down into 3 main types, 3 main categories. There's the ones that occur in the Lower East Drift Zone, okay, associated with that eruption. There's the ones at the summit, near the Caldera, associated with the collapse of the Caldera. And has anybody gone and seen that? In the park? Yeah, it's very different, right? And then the south flank. And now all these south flank ones are associated with the magnitude 6.9 earthquake and its aftershocks. So they have distinct characteristics about them. And if you want to hear more about this, I have an after dark in the park talk in the national park at the end of the month that we'll delve into this more. And, but if you look at these colors here, this shows the amount of earthquakes over time, or if you can read it over the date. So this is starting in January of 18, and then in May, everything takes off. And then by August, it shuts off. So May through August, those 3 months is when it was active. And if you look here, the red ones first, they pick up, and for only 3 weeks, where it was the area down here really active. For 3 weeks, when all those fissures were forming, covering up those homes, creating new lava flows. That's when all the earthquakes happened. But then once that was established, once Fissure 8 took dominance of the system, notice how those earthquakes just dropped off and just tailed off to low level. It was pretty interesting. Now, and only 1,500 of those recorded at this magnitude level. Now, the south flank is another story. Magnitude 6.9 earthquake happens. Takes it longer to die down, lots of aftershocks, which are still going to this day. Notice how it's not quite going back down to the level it was before. So that's another interesting observation. And this is basically showing that the south flank of the volcano at Kilauea, and we can measure this with GPS, is more mobile now than it was before the eruption. So it's actually more free to move, and in the process sometimes create these smaller earthquakes than it was prior to the eruption. And then finally, the big story seismically was the summit. We'll talk about this in the next slide. But this is when, so notice how the blue color here did not pick up in the beginning. It's, slightly, but it didn't really start until about a month into it. Then it started to pick up. So once enough magma had drained away beneath the summit, that's when the caldera started to collapse. And that's when all these earthquakes really started to take form. And now the 6.9 earthquake was large, the biggest in more than 40 years, and very severe shaking. And I remember diving under my desk, and it was a really exciting day. Certainly made the news. Here's a Tribune Herald article about it, talking about some of the effects. But it didn't make a big splash, for obvious reasons, because the eruption began just the day before. People were evacuating their homes. There was lava on the ground, and it's a triage situation in a certain sense. And so the public's attention did not dwell on this very long. But it's definitely a very major earthquake in the grand scheme of things for Hawaii. And it's hard to see here. This is a figure from a paper that came out in Science last year, and it's showing how the magma underground actually pressed sideways on the flank of the volcano, and that's what caused this fault to give, we think, and create the earthquake. It might have been ready to go anyway, but this is the push it needed to start. Okay, I promised to talk about the summit earthquakes a little bit, and this was one of the more surprising or novel things about the eruption from an earthquake standpoint. No one had ever observed this incremental caldera collapse in such great detail. And the Hawaiian Volcano Observatory has a really dense seismic network of monitoring stations around the summit where we could record all these earthquakes very well. And you can see here, these blue lines are the number of earthquakes per hour, okay, throughout that period of the eruption, throughout these 3 months of the eruption. And you can see sometimes you'd have as much as 150 earthquakes an hour happening in this region. But notice how it would rise high to a peak, and that's when basically this roof of the caldera is wiggling. As the magma's drained away, it's not supported very well, it's wiggling a little bit, creating all these earthquakes. It can't hold itself up any longer, it falls. It falls down several meters, 10 feet, something like that. And then everything goes quiet. It's happy again. It's stable. It's on more solid ground. And that's when this rate drops off until the magma is still draining away. It's not supported as well. It starts to wiggle again. It starts to create the earthquakes. It rises back up at the rate of the earthquakes until it falls again. This happened 62 times. And each one of these measured about a magnitude 5 in energy release. 5 point something on average. Very remarkable. This is a time-lapse video of the caldera showing from April through August what it's doing. So that's 1 photo per day, I believe. We'll watch it one more time to see what it was like before. You see the explosions happening with all the gas and ash early on. And then it just falls in on itself. The crater increased in volume by about 15 times, by depth by about 6 times, by width 3 times. If you have not seen it, go see it. So how unusual was this seismicity in the summer of 18? This is one way to look at it. So this is showing 20 years of earthquake counts from our catalog. So I asked my earthquake catalog how many earthquakes are happening per month, and that's what these blue lines are. You can hardly see here, but normally we have a few hundred earthquakes, up to maybe 1,000 earthquakes a month. Okay, remember the plot in the beginning of this talk when I showed the last month of earthquakes? It was 1,600, I think. And then here is the summer of 18. This is how unusual it was. We got about 3 years worth of earthquakes in 3 months. And we haven't looked at all of them. It's going to take us years to look at all these earthquakes and actually analyze them. And you can see, though, notice how now, over the past year and a half, we're at a higher level of seismicity in terms of numbers of earthquakes than we were before the eruption. So the volcano, the island, is still adjusting a lot. They're still creating a lot of earthquakes, relatively speaking. So how do we monitor these earthquakes? Well, in HVO, we have a number of ways we monitor the volcanic activity. So my piece of it is just one of many. So my piece is monitoring the earthquakes, but we have other scientists who monitor other things. And by taking all these types of data into account, we have a good picture of the volcano is doing. So this includes the shape of the volcano, how it's inflating, it includes the gases that are coming out, even includes the sounds that it makes, etc. Increasingly, we're using satellites and drones more to monitor from the air, from space. So this is just one piece of the picture. But from the seismic side, I broke it down into about 4 or 5 steps. So first you have to record the earthquakes on your instruments, your seismometers. You have to get the data back. You have to be able to use it. Then you analyze the data so you can learn about it, what's going on, and then tell people about it. And of course, do something about it if it's a problem, like drop, cover, and hold. So here, this map shows where our stations are. All the red triangles are locations of majority of our seismic stations. It's about 100 sites on the island. You can see they're concentrated on Kilauea as well as Mauna Loa, but they're scattered around as well. And so this is what I take care of, and this is what we use to monitor the earthquakes. This has changed a lot over time, and Thomas Jagger, who founded Hawaiian Volcano Observatory, the museum famously is named after him, was one of the people at the forefront of seismology back in the early part of the 1900s, developing the instruments for the first time. There's a photo of him in the Whitney Vault, which is behind the Volcano House in the National Park, developing some of the very first seismometers ever made. Here is an example of what one of our stations looks like today, up on the summit of Mauna Loa in the snow, with solar panels and Ethernet radios and batteries and very, very modern telecommunications infrastructure on our stations. And the instruments are all digital and computer-based. So speaking of the telemetry, the next cog in our wheel is getting the data back. And HVO actually operates its own private area network, if you will. Its own, it's like a cell network that's just for our data. It uses radios, uses microwave range radios. This is what one of the telemetry hubs looks like. But our data is shooting around the island, getting collected at places like this, and it comes back to the observatory where we analyze it. And how do we analyze it? Well, we have to triangulate where the earthquake occurred. And so we have a team of seismologists whose main job is to look at all the data streams coming in every day and to verify that the computer has found the arrival times of the earthquakes properly, and then adjust this as necessary to find when the earthquake occurred. And if you want to know the details, or at least roughly, here's how it works. You want to find when the P wave, the first wave, arrives at a station. When did the shaking begin at a station? We can measure that. And that's a time. And if we multiply a time by a velocity, which is the speed that sound travels in rock, you can measure that in the lab. You can knock on a rock and you can listen on the other side, and you can figure out the velocity that it took for that wave to travel through that medium. And scientists have done that, so we know the velocity of the rock. If you multiply those, you get a distance. Same phenomenon as if you're driving your car, you're trying to figure out how long it's going to take you to get somewhere. You know your speed, how much time you have, how far can you get. Do you run out of gas, for example? So that's the basic idea. These distances are circles. They become the radius of how far away that earthquake could have been from that station. If you do that at enough stations where the circles overlap, is your earthquake. So in principle, this is how we locate earthquakes. The computers help a lot. The computers do the number crunching, and we just provide the eyes and the expertise to see when this happened. And of course, the last step is getting the word out. This goes to the website. You can subscribe to something called the Earthquake Notification Service. Who gets that on your phones? A few of you? If you haven't heard of it, you can go to the USGS website, look for Earthquake Notification Service, or ENS. That's the link. And you can set up how to get it on your phone. And you'll be one of the first to know. As well as the HVO website. There's also the Earthquake Center website, which is the Colorado. Now, the final step, the astute people may know, is, well, what about the response step? Well, that's what this section is about. What do you do with that information? If it's a small magnitude 2 earthquake, you don't need to do anything. But what if it's a bigger one? So, because as we know, it's not if, but when the next big earthquake is going to happen. We know every roughly 10 years there's going to be a damaging earthquake here. There are some of them that I talked about, as well as some other ones that I didn't talk about. So the main thing is drop, cover, and hold on. So if the earthquake is so strong you have trouble standing up, that's your cue to drop down, because you might fall down again. And you'd rather get down yourself than fall down and get hurt, right? So dropping down is really important. Just get on your knees, get on the ground, however you want to, however you can. And ideally cover up. So you get under a table, under a desk, something like that, so that if the roof starts to fall, especially things like these ceiling tiles, anything like that that's weak can fall down. You don't want it to hit you in the head. So have a shield over yourself. That's why you cover up. And the reason you hold on is because the shaking can be violent enough that the table you're under might tip over, or it might shake its way out from over you. You know, it might shake its way sideways, and then you wouldn't be under it anymore. So just hold it over yourself, and just, you know, this will be tens of seconds, and then you'll be done. And once this happens, once it's all done, you can go. Usually we say go outside, because there could be aftershocks, and weakened material could fall down if it didn't already. So drop, cover, hold on, and of course if you're at the beach, get away from the water. So if it's one of these earthquakes that's strong enough you can't stand, well, it may be strong enough to make a local tsunami. Just get away from the water. You know, you walk about a quarter mile, walk for 10, 20 minutes if you want to be extra safe. You'll be okay. There's more information in the, yes?
What would be the time that it could generate a local tsunami? Let's say from a 6.
Well, the tsunami itself will be generated right away, and the speed of the tsunami is depending on the depth of the water, and so the deeper the water, the faster it travels. So when it occurs close to shore in shallow water, the speed is somewhat slower, which buys you some time. So if the earthquake occurred on the south flank of Kilauea, the tsunami would actually have to wrap around the island to get here, which could take about 15 minutes, 10 or 15 minutes, depending on at what depth it occurred, away from the coast. If the earthquake were, say, a South Kona kind of, or a southwest flank of Mauna Loa earthquake on this side of the volcano, you might have as little as 5 minutes before it would reach you. So that just gives you a rough idea. Folks on Oahu would have about 30 to 35, 40 minutes around there. Okay, so there's a pamphlet in the back called Earthquakes in Hawaii, right there, that you're all welcome to take home with you. And of course, you can learn a lot more on our website. In the Great Hawaii ShakeOut website, if you've not heard of this, go check it out. There's a lot of material there on preparedness, on safety, on different scenarios. What if you're disabled? What if you're at a school? What if it's in an office? A lot of what if scenarios are there, and there's good materials for you for all those sorts of situations. And the Great Hawaii ShakeOut coordinates the world's largest earthquake drills every October. And you or your business, your organization can sign up to be counted in the earthquake drills, where tens of millions of people nationwide participate in those every October, just to get practice with drop, cover, and hold on. The other thing I wanted to remind everyone today is to please submit Did You Feel It reports. Who knows what Did You Feel It is? I see a few hands, a few no's, okay? So it's a service on the USGS website. You can go to earthquake.usgs.gov/DYFI for Did You Feel It? And if you feel an earthquake, it just asks the question, did you feel it? You say yes or no. And if you want to, you can answer a few additional questions that say, well, did things fall off the walls? Were there cracks? And ask some additional questions if you want to answer those. And then it helps make maps like this that show the amount of shaking. And we can't have seismometers everywhere. Remember my map of the red triangles of where we have instruments? They're not everywhere, but there's a lot more people. So you guys can be little seismometers filling in the gaps on our maps. And it's really valuable to us to help us do that. Thank you very much for your time. If you have questions, let me know. Anything, I'll be here for about 15 more minutes if you have questions. Thank you.